Hello students, and welcome to the pre-lab video for torque. You know, if I have an object and it can pivot about a particular point, and suppose I apply a force to the edge, the force will have a tendency to rotate the object, obviously, and it motivates us to define a new quantity, and that is torque. If we take the distance from the point of rotation to where the force is applied, and we refer to that distance as the lever arm, and we multiply that by the magnitude of the force, we'll get a new quantity we refer to as torque, and the SI unit would be the Newton meter. Torque is a vector quantity, but for us, these torque vectors will always only be in one dimension, so we can keep track of their direction with a sign, either positive or negative. And the convention we will take, if the force generates a counterclockwise torque, or it would generate a counterclockwise rotation, it is a positive torque. If it would generate a clockwise rotation, it will be a negative torque. Now, Newton's laws extend to the world of torque. So torque is like the rotational analog for force. And it turns out if we have an object in static equilibrium, just like the summation of all external forces acting on the object will equal zero, it turns out the summation of torques acting about any one particular point on the object also equals zero. And we're going to verify that fact experimentally today with a very simple device, a beam and a fulcrum with some hanging weights. So let me demonstrate how we would use this very simple device to you. So for us, our beam will be a meter stick, and it's very convenient to use because already it's laid out in centimeters, so we can easily measure the lever arm. This is the fulcrum. It's the thing on which the meter stick balances. And you see these little metal things that slide onto the meter stick. We call these knife edge clamps. We can do two things with them. They have ears, you see, that come out, so we can use one to balance the beam in the fulcrum. And you can also put hangers on these little ears, and you can attach them to the beam and use them to hang weights. So the game is to hang weights at various points, and of course these are forces, and they're acting about a lever arm and can rotate the beam one way or the other. So we're going to try to set it up in static equilibrium, add these torques up, and confirm that they sum to zero. So the first thing you will do in this lab is you want to find the center of mass for your beam. That is, on average, where the mass of the beam is located. You may say, well, this stick is fairly uniform. It will be at 50 centimeters, and that's where I have the knife edge clamp located now. That is not always the case, so it may be a little off 50 centimeters. So I have it at 50 centimeters, and it is fairly well balanced. It is actually quite difficult to get the beam to perfectly balance in the fulcrum, so anywhere even close to balance like this is quite good. So I've found my center of mass, and then I would record that. Now there are several things we could do. So let's start by adding two masses, and perhaps you're told to put these masses at particular locations, so particular distances from the pivot point. So I'm going to put some on here, different locations. And see if I can achieve balance. So these distances were given to you, and then maybe one of the masses is determined, and you're told, hey, find what mass you need here to find equilibrium. So let's see if we could do that. We'll begin to add mass there. See, there I go too far, so I need a little less mass. So I'll get my 1 gram masses and see what we can do here. So I'm pretty close right now. It can be a little difficult, so try not to get too frustrated with it. We do not have half-gram masses in the lab, unfortunately. So that's a pretty good case of equilibrium there. So I would determine the weight here, including the little knife edge clamp and the hanger. I would determine the weight here, have these distances, and I would see if the summation of torques would equal 0, and it should in fact do that. So another variation on this is, to have the two masses fixed at a particular value and find out where you need to move maybe one of the knife edge clamps to achieve equilibrium. So that's what I'm going to do now. I have the two masses fixed, so I'm going to move one. Obviously this one needs to come in a little bit, and I keep adjusting. And there I finally have it. So again, I would record the weight here, the two distances, and I would see if the summation of torques would equal 0. Here's a third thing we can do. We can move the fulcrum away from center of mass and see if we can find balance. So let me do that. I'm just going to move it 2 or 3 centimeters away from center of mass. And now the interesting thing is we have 3 torques. We have the one due to this weight, the one due to this weight, and the one due to the weight of the beam operating through center of mass, which is now 3 centimeters from the pivot point. So can we achieve balance here? So we see we need more weight on the left side here, so I'll add a little bit with my slotted masses here. So here I go, adding mass, adding mass, adding mass. There I went a little too far, so maybe a couple of 1 gram masses will get it for me here. Pretty close now. Will one more do it? It looks like one more pretty well did it. I'm pretty close to equilibrium there. It's hard to get it completely perfect. We just do not have half-gram masses, unfortunately. Sometimes you need those. That's pretty close to equilibrium. It's hard to get all of them exactly perfect. So I would have 3 torques in this case. 1, 2, 3. All 3 should sum to 0. So you'll do a variety of these different exercises in this lab and verify that the summation of torques goes to 0. And it's a very simple lab, but a very important lab. And students struggle a little bit with torque because, unlike just adding forces together and see if they sum to 0, magnitudes of forces, or vector forces rather, you have to multiply the force by a lever arm when you add torques together. So there's this extra step that makes it a little more difficult, a little more abstract for students. So I hope you think about this lab and watch the video several times before you come in and try to do it. So I think that's all for now for the torque lab. So I look forward to seeing you in the lab.